So, in our last lecture we looked at the simulated annealing technique for placement of the blocks. So, it was a technique which was using some analogy from the process of annealing of glass or metals, the way they are crystallized. Now, in this lecture we shall be looking at another method for placement which again takes analogy from another problem of physics, namely the property of springs, the elasticity of the springs. Some well known law you must have heard of, Hooke's law. So, it is basically based on some property of springs and their equilibrium condition. Let us look at that problem. This method is called force directed placement. Now, as I said, this method explores the similarity of analogy between the placement problem and a very classical problem of mechanics, which is a system of bodies attached to springs. I shall take an example to illustrate. So, there are a set of bodies which are attached to springs. This is the analogy we are drawing here. So, we shall come to it a little later. This is an analogy with respect to the placement problem, where I say that the blocks that we want to place, which are connected to each other by nets, they exert attractive forces on each other. Magnitude of the force is directly proportional to the distance between the blocks, which is analogous to Hooke's law in mechanics. Let us try to explain this first. So, we start with Hooke's law. So, what is Hooke's law? So, Hooke's law relates to the property of a spring, how stretching or contracting a spring exerts force on a body or a mass which is connected to the spring. So, let us see. Suppose we have two masses, let us call them M1 and M2, that are connected by a spring. So, what you can do, okay, let us say the distance between these two bodies is d. So, for a spring, you know that if I stretch this spring M2, if I pull it in this direction, release, it will again come back here, or if I push it in this direction, so and if I release it, it will again come back in the original position. So, whenever I pull or push a spring, a force is exerted which tends to move it back in the other direction, right. So, the force exerted on the spring is proportional to the distance that separates the two ends of the spring, this M1 and M2. So, you can write F equal to some constant k into d, where this constant k is called the spring constant. So, this depends on the quality of the spring. If it is a very strong spring, the value of k will be very large, but if it is a very weak spring, the value of k will be less. So, this proportionality between F and d, this will hold for this spring material within limits of its elasticity. See, if you pull this spring beyond a certain limit, then some permanent damage might take place in the material. There can be some permanent deformation which we say is beyond the limit of elasticity, which means if you release it, the body M2 will not come back exactly to its original position. Some part of the spring might get damaged permanently. So, that is why we are saying that within limits of elasticity, the proportionality of F and D holds. Okay. So, this is for two springs. Now, let us look at the placement problem where we have two blocks, let us say a block B1 and a block B2, let us say there is another block B3. So, what I consider is that let us say between B1 and B2 there are 5 connection wires and nets, there are 5 nets which are running. Between B2 and B3 there are 2, between B1 and B3 let us say there are 3. So, I can draw an analogy. So, what I say is that you see in the placement problem what are you trying to do? The two blocks which are more strongly connected together, we try to put them as close together as possible, but if they are not so close strongly connected, they may be put a little further effort, no problem. So, what I am saying is that this problem, can I model it equivalently as 3 bodies B1, B2 and B3 which are connected by 3 springs whose spring constants are k equal to 5, k equal to 2 and k equal to 3. Because this particular spring is the strongest with the highest value of spring constant, it will pull B1 and B2 closer together. So, if you leave this system of bodies to move around freely, they will finally settle down into a configuration which is the so called equilibrium condition. Okay? The net force on each of the bodies will be 0. There can be other springs also connected. So, I am not showing, I am only showing 3, because if it is only 3, the equilibrium position will be they will all come all together, but there are other pulling forces in other directions also. Okay. So, the analogy is like this: we have a spring, we have the interconnection lines. Now, the analogy is that Hooke's law says force will be proportional to the distance. Here also the same thing. Let us say this is the distance d between the two blocks B1 and B2. So, the attractive forces between B1 and B2 will be equal to number of lines, this is your k multiplied by the distance, exactly like Hooke's law. So, this kind of similarity or analogy we are drawing, and using this principle we are framing or formulating this particular method for placing the modules. Okay. So, let us come back to this slide again. So, we are saying that the blocks connected to each other are supposed to exert attractive forces just like as if they are connected by springs, as I said. Magnitude of this force is proportional to the distance, this also I have said, and when you leave them alone to move around freely, the final configuration will be the one in which the system achieves equilibrium. So, when I say system achieves equilibrium, let us take another example to illustrate this. Let us say I have 3 bodies, okay. Let us call them blocks B1, B2 and let us say B3 is here. So, I am assuming that these 3 B1, B2, B3 represent blocks which are already placed on a floor plan. Let us say a full custom design where we have placed B1 here, we have placed B3 here, we have placed B2 here. Now, what we are now contemplating, a 4th block B4, we are trying to find out a good location to place it. Okay. So, this B4 I am denoting by a body B4, I am showing it in a rectangle, which as if is connected by springs to these 3 already placed blocks B1, B2, B3. So, their connectivity can be K1, K2, K3. Now, what I am saying is that in this condition I release B4. So, let B4 move around and reach a final position which will be its equilibrium position. Let us say, suppose the final position of B4 is this. So, if you release B4, the final position of B4 will be this. So, B1 will be connected this will be connected, this will. So, in the final position, the total force exerted on the block B4 will be equal to 0. This is the definition of equilibrium, right. So, when you have this equilibrium, we say that we have found out the best position to place block B4. This is the basic concept behind force directed placement, right. So, in general, if you just again look at it, whatever I have said, that if there are two blocks like this, let us say B1 and B4 in general. So, you have the interconnections, the weight will be, let us say W14. So, how many lines connecting this? Distance between these blocks, let us say, is D14. So, the force of attraction between these two blocks B1 and B4 will be W14 multiplied by D14, just exactly like Hooke's law, whatever it says. It will be proportional to the distance. W14 will be the constant, right. Okay. So, then a cell connected to several other cells will experience a force. Well, I will be explaining this expression. Let me work out a simple scenario first, it will be easier to appreciate. Let us say I have a scenario like this, where I have a block I which I want to place. There are already 4 blocks which are already placed, let us say 1, 2, 3 and 4. So, each of these blocks is generating some attractive forces. So, 1 is trying to attract I towards itself, 2 is trying to attract I towards itself, 3 is trying to attract I towards itself and 4 is trying to attract I towards itself. Now, it depends on the let us say, let us call these weights Wi1, Wi2, Wi3 and Wi4. So, the total force that will be exerted on the block Fi will be denoted by Wi1 into Di1, where Di1 is the distance, this is Di1, Di1. Similarly, this will be Di2, this will be Di3 and this will be Di4. So, the total force exerted on I will be Wi2 Di2 plus Wi3 Di3 and Wi4 Di4. Now, what you want to do is that you will have to solve some equations and find out the location for I for which this force will become 0, because some of them will be pulling in the right direction, some block will be pulling in the left direction. So, there will be a sign involved, plus and minus. The sum total has to be 0 both in the x direction and also in the y direction, right. So, this exactly what I have shown here is mentioned in the slide in a general form, where a cell is attracted by other j number of cells. So, it will be summation over j Wij Dij this will be the total force, where Wij is the number of connections between I and j, that is the weight of the connection, and Dij will denote their distance. Now, what I have just mentioned, if the cell I is allowed to move freely, so it will be moving towards the direction of the dominant force, and in its final position, which is sometimes called the 0 force target location, the resulting force Fi will become 0. So, if we allow the cell I to move freely, it will automatically come and rest in its final so called 0 force target location. So, our objective is to find out the coordinate of the 0 force target location, so that we can decide which is the best location to place that block. Okay. So, in this way, if you carry out an iteration one by one, you place the cells. So, when all the cells move to their 0 force locations, the total wire length is expected to be minimized. This is what we are trying to do, because the two blocks which has maximum number of wires between them will be having maximum force. So, they are expected to come closer together. Okay. This is the basic idea. So, let us make a simple calculation. So, a force, from mechanics, a force will be having its x component and y component on a 2-dimensional plane. So, we are separately equating the x components and y components of the force to 0 and trying to solve for the coordinate. So, for the cell I, let us assume that xi 0 and yi 0 will represents the 0 force target location. So, then the total force exerted on cell I in this final location in the x direction will be Wij xj 0 minus xi 0. This j is all other blocks, and I is the, okay, for j this 0 is not required actually. So, you need 0 only for I. For I, the because I am assuming that all the other blocks are already there in the 0 force target location, that is why I am showing 0 here. But right in this equation we are more interested in xi 0. So, distance between the two blocks in the x direction will be xj minus xi multiplied by weight. Similarly, in the y direction, distance between the two blocks will be yj minus yi 0 multiplied by weight. So, if you equate these two separately to zeros, that means the net force along the x direction, along the y direction will be zeros. If you solve it, you get the value of xi 0, this xj 0 I am writing xj, this yi is 0 I am writing yj 0. So, the final location is given by x and y values by expressions like this. So, if I know the coordinates of all other blocks and their weights of connections, so we can calculate the value of the 0 force target location. But of course, we should check explicitly that there is no overlap when we are generating the target coordinate, because you may be generating some target coordinate which is already occupied. So, we will have to put the block in some nearby location. Okay. Fine. So, let us take a small example to illustrate. Well, the problem is shown in the diagram on the left. You ignore the diagram on the right temporarily, because this represents the final solution, but we shall be arriving at this. You see, in this example I have shown 4 input output pads indicating in, out, VDD and ground, and 1 gate, right. So, I am assuming for simplicity that I have a 3 by 3 grid like structure, a very small sub problem for illustration, where the 4 pads are already pre-placed in the 4 corner rectangles. VDD is here, out is here, ground is here, and in is here. Now, our problem is to find out the best location to place this inverter, this gate. So, there are 1, 2, 3, 4, 5 locations available. So, out of these 5 locations, which is the best location to place this gate? So, whatever is available here is that the weights of the wires are given. Well, these numbers are just for illustration purposes. Do not think that why VDD weight is 8 and ground weight is 3, these are nothing, just some numbers. So, let us say W VDD, this weight of this line is 8 and W and out is 10, W and in is 3 and ground is also 3. So, our objective is to find out the 0 force target location of this gate, right. Let us see. So, this is our 3 by 3 grid. We are assuming that 0 0 indicates this cell, this is 1 0, 2 0, this is 0 1, the 1 1, 2 1, 0 2, 1 2 and 2 2, that is the convention. So, just we are following that equation which we derived just some time back. Let us first calculate the 0 force x coordinate according to the equation we derived. So, Wij values are already known, 8, 10, 3 and 3. So, the numerator Wij into xj will be, there are 4 j's VDD, out, in and ground. So, W VDD x VDD plus W out x out, W in x in and W ground x ground. In the denominator just the sum of the weights. So, you put the values, the weights are 8, 10, 3 and 3, W VDD is 8 and x VDD. For VDD what is the x coordinate? 0, it is 0 2. For out the weight is 10, the x coordinate is 2, 10 into 2. For x in the x coordinate is again 0, 3 into 0. For ground x coordinate is again 2, 2 0, 3 into 2. So, if you calculate it comes to 26 by 24 is 1.083. Similarly, if you calculate the 0 force y coordinate using this equation, it will be similar. So, the equation will be like this, y VDD, y out etc. So, this y VDD 8 into, for VDD y coordinate is 2, 0 comma 2, y out is also 2, but in and ground the y coordinate is 0. So, it is 0 and 0. So, this comes to 16 and 20, 36 and this is 24. So, you get 1.5. So, the 0 force location has been calculated as 1.083 and 1.5, and if you do a round off it comes to 1, 2 nearest integer values. So, 1, 2 will be this cell. So, the final solution is shown. So, for this particular problem this gate has to be placed in this location in the grid. Okay. So, this is the basic idea behind the force directed placement, you can say, where the sub problem that we had looked at right now is that some other j number of blocks are already placed. I am trying to place a new block I. So, what should be the coordinate of I such that the total force that is exerted on I by the external j blocks will be 0, both in the x direction and also in the y direction. Okay. Now, so we have looked at the sub problem for placing one block only, assuming the other j blocks are placed. Now, this approach can be used for constructive placement. Constructive placement means I have, let us say I have 100 blocks, I want to place all of them. Constructive means I am placing them one by one in some sequence. So, slowly I am constructing the placement. Constructive means something which grows in size as it proceeds. Okay. So, the constructive placement is very simple. You start with some initial placement, you select well, initial placement is null, nothing is there. So, you select one module at a time, computes its 0 force location and try to place it there. Well, of course, there are some heuristics using which you can iterate to improve upon the solution obtained. Now, the order in which you take these cells for placement, it can be either random or it can be driven by some heuristics. Like for example, at every stage you consider all the remaining cells. Like for example, out of the 100 I have already placed 40 cells, 60 are remaining. So, I calculate for each of the remaining 60 cells for which the value of Fi is coming to be maximum. So, if I have come up with a tentative placement, so for the tentative placement which is coming to be maximum. So, you select the cell for which Fi is maximum and try to generate a new location for it by calculating. Of course, here I am assuming that I am starting with some kind of a random placement, not placing them one by one. So, I am randomly placing the 100 cells on the floor, but one by one I am considering them for optimization, trying to find out the 0 force location. So, there are a number of heuristics which have been proposed, that when you calculate the 0 force location of a block or a cell, say if you find that the 0 force location is already occupied by another cell Q, then this cell under consideration, let us say P, you have several options for this. You move P, well, you cannot put P into Q because Q is already occupied. You move P to a location which is close to Q, either right, left, top, bottom, somewhere there. Number 2 is you evaluate that what if we exchange or swap P and Q. So, if you exchange P and Q and see that the cost is decreasing, then we can just accept this swap. Ripple move means we do some kind of a rippling or chain reaction, like you place the cell P in the location that has been computed, which is occupied by Q, and for Q with the new location of P you compute the new 0 force location for Q. You place Q in that location. If you see that location is also occupied by another cell R, you find the 0 location for R. In this way you repeat till all the cells at the end are getting placed. And finally, a chain move is you do not recompute the 0 force location every time like in ripple move, but you move the cell P in the computed location and the cell Q which was occupying that location earlier, you move it to an adjacent location. If the adjacent location is also occupied by some other cell R, you move R to the adjacent location and so on, like you are shifting all the cells basically, okay, until a free location is finally found. So, we have seen the force directed scheduling and constructive placement case, where using means analogy from springs, the way forces are exerted by springs on a body, we can also find out the best location to place the blocks. Now, there has been a number of such placement tools which use this kind of heuristic based on force directed placement to actually find out the location for the different blocks. So, with this we come to the end of this lecture number 13. So, thank you.